Okay.
Then hello everyone to today's seminar on interval methods and control engineering. And it's my great pleasure to welcome our speaker today. Our speaker today will be Awais, and he received his Bachelor of Science degree in Electronics Engineering from the University of Engineering and Technology in Peshawar in Pakistan. And afterwards he did his Master of Science degree also in Electrical Engineering from the University of Engineering and Technology in Lahore in Pakistan, and his PhD at the Guangdong University in China. And he's also currently in China, where he's doing a postdoc research fellowship at the Shenzhen University. And we're looking forward to your presentation now on interval estimator design for LPV systems with an extension to SEIR models using the observability matrix. Now, Awais, the floor is yours.
Oh, well, many thanks, Andreas, for inviting me to this online seminar on interval methods and control. As you mentioned, the title of my talk is Interval Estimator Design for LPV System, and with an extension to the SEIR Epidemic models, and we will use a new technique that is based on the observability matrix. So the overview of my talk is, first we will introduce, because I am going to design interval estimator for LPV systems. So first we will introduce the LPV systems, what are LPV systems and why they are important. Then we need to, in the second half of my talk, we will extend our design method to the SEIR epidemic models. So then we will introduce SEIR epidemic models. And then why we use interval estimator instead of classical observer. We will also explain in few minutes about this as well. So after that, we will have problem formulation for LPV discrete time system. And then we need some definitions and assumptions for that to design the interval estimator. And after that, we will start our main results from contribution, then how we will convert the system to the input-output model, then main results. And after that, we will finally design our interval estimator. Then we will extend our design model to the SEIR epidemic model. So we will apply our design model to the SEIR model. And after all these things, we will show by simulation the efficiency of the proposed method compared to the other methods that are already exist in the literature about the interval estimator designs. And finally, we will conclude our talk. So first of all, why we need to design the interval estimator for the LPV system. So LPV system are a kind of system that is slightly different from the LTV system, because in LTV system, the dynamics of the system depends upon time, where in case of LPV system, we have non-exogenous, non-stationary parameters. So with the change of the parameter, the dynamics of the system change. So it can be anything, not only the time. It was introduced for the first time by Shama in Athens in 1988. And one of the most important advantage of introducing the LPV system, that it is a bridge between the linear and non-linear systems. Like if we design a controller for a linear system, so how we can apply the same controller design with some minimum changes to the non-linear system. So before applying to the non-linear system the same controller, we change the non-linear model to the LPV systems. And this is one of the main advantage of the LPV system, that it is a bridge between the linear and non-linear systems. So xt of 1, it is a non-linear discrete LPV system. Xt of 1 is equal to a zeta of t, x of t plus b zeta of t, u of t plus e zeta of t, w of t, and y of t is our output equation, which is c zeta of t, x of t plus d zeta of t, u of t plus f zeta of t, w of t. So if we see the given model, LPV model, our model is not only dependent on time, it also depends upon a non-stationary parameter, which is zeta of t. Okay, so the main difference, what are the, now we will show the connection between the linear and linear time invariant and linear time variant system compared to the LPV system. So it is very obvious as compared to the LTI system that LPV system is parameter dependent, while LTI system is independent. It is not, it doesn't depend upon the time or anything else. So it is very obvious difference between the LPV and LTI system. But compared to LPV and LTV system, we can, the more pronounced is the control design or its synthesis, how we use and how we synthesize our control model for the different types of the systems like LPV system. LTV system is time varying system that is dependent upon time only, while LPV system, the varying parameter can be anything. And it is like if the LPV system is a specific class of hybrid dynamical system, just like in switch system, the switching material can be anything, not only the time parameter, that it can be anything with the passage of time. And for example, if we have jump system can be viewed as one kind of the LPV system. So this is one of the most important use of the LPV system, that why we need LPV system and why we need to design the interval estimator for the LPV system. There are many applications of LPV systems in the real life, like for example, flight control, missile autopilots, air electricity, automotive systems, energy, IC manufacturing, diabetes control. So all these are some specific application of the LPV systems. Okay, our next topic will be, the second part of the talk will be based on the SEIR epidemic model. So the SEIR epidemic model is, it is a suspectable, exposed, infectious, recovered model that was first developed by Kermick and Mechatronics in 1927, and it was applied on many kind of infectious diseases like measles, mumps, rubella, Ebola in 2014 Ebola outbreak in the North Africa. So why we need the SEIR epidemic model, why we need to design the interval estimator for the SEIR epidemic model, because nowadays is the, just like for the example, we can take the example of the COVID-19. It is a kind of infectious disease, and it can spread very fastly. So before the spreading, we need to detect how it is going, how it is spreading. So if we detect the outbreak, then we can make a strategy how to control the pandemic or how to control the given epidemic. So for making this some strategy, we need to some estimation tools to estimate the outbreak, and then according to the estimation, we can make a strategy to control the given model. So basically, SEIR epidemic model is basically composed of the 4 portions. We can divide it into 4 different portions. Number 1 is susceptible humans. It consists of those humans who are not infected yet, but they can be infected in future. Like they are not immune, so they are always at risk of infection. So they can be infected with anything in the future. So they can be infected. Number 2 is exposed. Exposed people are those people. The second compartment, we have people, they are exposed who are infected, but they cannot infect others. Like for example, like those people who are infected, and we put them in quarantine, so they cannot infect other people. So these kind of people will fall in the exposed compartment category. The third one is infectious human. Those humans who are infected, and they also can infect others. Maybe before the detection, nobody knows that they are infected and they can infect other people, or in case when they are asymptomatic, like they didn't have any kind of symptoms, and they didn't know that they have such kind of infection and they can infect other people. The fourth one is they recovered humans. Recovered humans, like they are immune, they are naturally immune, or they are recovered from the infections. So when they are recovered from the infection, they become immune to the infection, or sometimes people have a naturally capability of immune to the given disease. In the block model, if we can all these four compartments we can draw in a block model like this. That is for the susceptible compartment, E is for export compartment, I is for infectious compartment, and R is for recovered compartment. Okay, so now the question is, why not classical observer? Why we need to design the interval estimator or interval observer? As we already have classical observer like Lewin-Berger observer, Kalman filter. All these observers are already in the research area and they are so developed. So why we need to use interval estimators? So the first we need to know that if we need to design any controller, all the states of the system are not available. So for that case, we need to estimate the unknown states in order to design the controller for any kind of system. So that's why we need estimation. That's why we need observers. It can be any kind of observer. This is the importance of the observer. And why not classical observer? So classical observer like Lewin-Berger observer or Kalman filter, when we have uncertainties that are unknown and its value are too high, so we cannot get the desired estimation what we want to for designing the controller. Or sometimes, like if for example, if you take the example of the Kalman filter, so for designing the Kalman filter, we need to know the exact properties of the disturbances or uncertainties. We need to know exactly how they behave in order to design the Kalman filter. But in some cases, or in many cases, we don't have the exact values of the given disturbances or uncertainties. We just know the given bound and the exact values are unknown to us. Then we cannot design the Kalman filter or Lewin-Berger kind of observers. Or another problem with these classical observers, that if the uncertainties or the disturbances are too high or too much, then we cannot get the exact value of the state estimation, or the classical observer, the estimated state cannot converge directly to the actual state. Or also in the monitoring, if we use in case of the fault detection and installation, in transit periods, these classical observers did not guarantee the exact monitoring of the fault detection in the transient periods. So that's why we need to design another kind of observer that can handle, or they can be use all these problems. And to solve all these problems, a new kind of observer, which we call it interval observer, interval estimators, or set membership interval estimators. These it is a kind of observer that generate two bounds, upper bound and lower bounds, and the exact value of the state is always in between these two bounds. It consists of two dynamic systems. One will provide us the upper bound and the other will provide us the lower bounds. And the distance or the deviation from the exact value from upper bound to the from the actual state, or the lower bound to the actual state, will give us the interval error. So we can have the interval error at any time instant. We will have the exact value of the interval error. So this is one of the advantages of the interval estimator as well. And the given system, the given figure interval estimation mechanism is given how the interval estimator works. To explain the given interval estimator problem, we use a simple example in order to give a good idea how the interval estimator or how the interval observer works. We have a non-linear kind of system x dot of t is equal to minus x cube of t plus d of t, where d of t is the state disturbances. The state disturbances are unknown but bounded, whose minimum value is -1 and maximum value is +1. So in this case, the exact value of the disturbance is unknown, but the bounds of the disturbances, we know only the bounds of the disturbances, and we only know the bounds on the initial conditions. We don't have the initial condition in this case. So if we put the for in case of very raw observer design, or a kind of intervals design, not observer, just we just show how the intervals are created, generated, and how these generated intervals, the exact value of the state will be between these bounds. So in a very simple thing, if we put the maximum value of the disturbance, so we get x upper bound minus x cube plus 1 with initial value of +2, and the minimum bound or the minimum value for this system is x dot of minus x dot minus t is equal to minus x cube of t minus 1, where the minimum value of the initial condition is -2. So if we put any value for any time of t, the exact value of x of t will be between these two bounds, x minus of t and x plus of t. The exact value will always be between these two bounds, and we will get the bounds on the estimated state. This figure is just it's not related to this above example, but it is just for explaining how the interval observer works. So here we will see that the green line, it shows the actual states of the system. The red dash line show the upper bound, and the blue dash line show the lower bound. This figure I took from my research paper that was published in 2019. So if we, and it was also for LPV systems with in that case, the uncertain parameters are unknown. So if we see, and our system also in that research paper, we also take the component faults in the system as well. So if we see from here, the estimated, the real states are always between the two estimated states, the upper bound and lower bound. And in that paper, we also show that after 100 t is equal to 100 seconds, there is a component fault in the system. So even in the presence of the component fault, still the estimated state is between the two bounds. Now, the interval estimators, because interval estimator is developed for more than a decade, even more than that. So there are many interval estimators, interval observer methods, techniques are available in the literature. So what we are doing now, like what we have done different than them. So mostly in the literature of the interval observer, most of the technique already exists or based on monotone system theory, or you can say the system should be cooperative, or the system must be positive, or if the system is not positive or not cooperative, we need to convert the system to a cooperative system by a technique known as transformation of coordinates. So in order to design the interval estimator or interval observer, our system should be cooperative or at least monotone system. So in that case, it is like very restrictive to design an interval estimator, because in real case, we don't have all the system are not cooperative, all the system or cannot be positive. So, and so for that purpose, we transform the system, we use a transformation of coordinates to transform it to a cooperative system if the system is not cooperative, but it is also not always possible, or even it is more time consuming, or it is very difficult to get the transformation of coordinates, especially when the systems are have a lot of states, like about 20 states. If we have a system of 20 states or 30 states, or like that. So the transformation of coordinates in that case being impossible sometimes, or even too difficult to get. So in order to remove these two strict restrictions from the design of the interval estimator, we propose a new technique based on the observability metrics that will also save us the computational time, and it is also more accurate as compared to the already existing techniques in the literature. And our proposed technique is less restrictive, because in our case, we don't need the system to be cooperative. We don't need the cooperativity condition. And if we don't need the cooperativity condition, so it means we don't need the transformation of coordinates. So we can design directly our interval estimator for any kind of system, if it is cooperative or not cooperative. The outcomes of our design technique is that we design the interval estimator for the LPV system, which is not too restrictive as compared to the already existing techniques in the literature. And we also extend our design model to the SEIR epidemic model, which is not fully considered till now. And so we use the observability metrics to design the interval estimator for these two kinds of models, LPV model and SEIR epidemic model. So this is the first part of our design technique of this talk. We take a system of LPV type of system. So first we design the interval estimator for the LPV system, and after that we will extend our design to the SEIR epidemic models. So first consider an LPV type of system shown below. Here the given LPV model x of t plus 1 is equal to a naught plus delta of a theta of t plus theta of t into x of t plus b u of t plus phi of t, and y of t is equal to, which is the output equation, output measurement, which is cx of t plus v of t. So x of t is the state vector. It's a real state vector. U of t is our input. Y of t is the output vector. This theta of t is the non-stationary parameter. Because of this non-stationary parameter, our system is LPV. So it consists of the vector of scheduling parameters. This psi of t, theta of t belongs to psi, and which is a real vector, consists of the scheduling parameters. Psi is the compact set of is a compact real vector with theta of t, and psi is bounded. A, B, A naught, B, and C are known matrices of suitable dimensions. Pi of t is the state disturbances, and V of t is the measurement noise. So we need to design the interval estimator in the presence of these state disturbances and the measurement noise, such that the actual state is always between the upper and the lower bounds. Before going to design the proposed interval estimator, we need some definitions. They need to be known, and we also need some assumptions in order to design the proposed interval estimator. So what is an interval vector? Just need to recall some definitions. Interval vector is we have x minimum value and x maximum value. So we have a value a such that x is greater than the minimum value and x is less than or equal to the maximum value. So it means that any value that is in between these two upper bounds, upper maximum value or minimum value, will lie inside the vector. We will need these two interval width in the proposed technique. So that's why we define these widths here. For a scalar vector, if we have any scalar, so the width for the scalar should be the maximum value minus minimum value will give us the width between these two scalar quantities. In order to get the width for the vector, so the maximum value among all these scalar intervals will give us the interval width for the given vector. So if we need to check the scalar interval for each and every point, and the maximum value of these scalar interval will give us the interval vector for the given vector. Okay, we need the following assumptions. Assumption number one, that the system should be observable. If in order to design the proposed technique, the system must be observable, and at least it should be full column rank. The given system should be full column rank, and the initial conditions should be unknown but at least bounded. And similarly, the psi of t, which is the state disturbances, these must be unknown, at least unknown but bounded, and also the measurement noises should be bounded as well. These are the definition of the bounded, unknown but bounded uncertainties and disturbances. And also we need to have the n-1 and n concatenation of the highest and lowest bounds of the disturbances and noise. These represent the minimum n-1 concatenation of the disturbance, and d positive represents the n-1 concatenation of the disturbances, maximum value of the disturbance. Similarly, v negative represents the n concatenation of the measurement noise, and v positive represents the maximum value of the n concatenation of the measurement noise. These vectors we will need to design the upper and lower bound on the state disturbances and measurement noises. So the goal is very simple. The goal is that we need to design an interval estimator that will generate two bounds, upper bound and lower bound, such that the actual state of the system lies between these two bounds. And we need to relax in the proposed net. We relax the cooperativity and the also avoid the transformation of coordinates that is not always possible. So we use the mathematical induction, interval analysis, and observability metrics, and avoid these strict cooperativity conditions in order to design the proposed interval estimator such that x of t lies between the x negative of t and x positive of t, means the upper and the lower bounds. So the first step is to the first step for designing the proposed interval estimator, we need to convert the given model into input-output blocks. So the above LPV system can be written in this form: x of xt plus n, where n represents the size of the model. It can be anything. N is 1, 2, 3. It is the dimension of the given system, so it can be any value. So xt of n is x of t plus n is equal to lambda of a plus x of t, lambda of a x of t plus lambda b sigma of u t to t plus n minus 1, sigma y of t to t plus n minus 1 is equal to lambda naught x of t plus lambda c sigma u of t to t plus n minus 1. We will define these matrices one by one now. Sigma u will represent the input matrix from u of t to u of t plus n minus 1. So it will contain the input vector, n blocks of the input vector, n blocks of the input vector, and the sigma y of t plus t to t plus n minus 1 represents the n block of the output vector. These are the n blocks, y of t plus 1 to y of t plus n minus 1. Lambda a represents the state transition matrix, which is equal to product of a plus a naught plus delta of a theta of t plus n minus 1 minus I. So this transition matrix consists of the products of all these matrices. Similarly, the reachability matrix, lambda of b represents the reachability matrix, which is equal to the product of delta a naught plus delta of a theta of t plus n minus 1 minus I into p. So it will represent, it will give us the 1 in the matrix, and it goes up to all these. Finally, it will goes to matrix B, vector B. So we will put here vector B, and we will get the reachability matrix. And this lambda of C, which is of the NP into we forgot to write here R. So it is a matrix of dimension NP into Mn, and it is given by the following values, where the first row is all 0, and second is C into B, and these all are 0. And it similarly it will goes up to a product C into product of a naught plus delta a theta of t plus n minus 1 minus I into B. So we will get this lambda of C matrix by this matrix. The given, okay, so after all these things, if we go to this equation from this output in block output vector, we get this states from this. We will get the state of the system in the input output block model as below. Just like here, the given system can be written in the input output block form as x of t is equal to lambda of 0. This represents the generalized inverse matrix of the observability matrix. In case of the square matrix, it is very easy. Just we use the simple method of getting the inverse of the matrix, because lambda of naught represents the observability matrix, where this symbol represents its inverse. So, but in case of the full column matrix, if the given matrix is not square but still it is observable, then we use the generalized inverse for the given matrix. And these are the output metric n blocks of the output vector, and this is the sigma u represents the n blocks of the input vectors, and lambda of C represents the matrix already given here. We will get the lambda C matrix, which is of the dimension in P cross Mn by this method. Okay, so if you don't have any noise, or if you don't have any state disturbances, so in that case, the state of the system can be written in this form: x of t dot is equal to lambda y of t sigma y of t minus n plus 1 up to t plus sigma lambda u of t sigma y of t minus n plus 1 up to t, where lambda y of t represents the output matrix given by this equation, product of a naught plus delta a theta of t minus 1 into the generalized inverse of the observability matrix, and it will give us the output matrix. The lambda u of t, which represents the input matrix, and that can be obtained using this equation, lambda of 1 minus lambda y of t into lambda c. Lambda c and lambda y of t is already explained above, whereas lambda 1 can be obtained using this equation. Product of a naught plus delta a into theta t minus I into b, and similarly from 1 to n minus 2, and then from I is equal to 1 to n minus 3, a naught plus delta a theta of t minus I n to b, and finally to up to 0. So this will give us this gives us the states of the system in case when we don't have the disturbances and uncertainties. Like, if in short we can say, if we don't have any exogenous signals, then we can directly get the states by this equation. But in our case, we have the state disturbances as well as we have the measurement noise. So we propose the following interval estimator in order to get the bounds on the actual states of the system. Xt of plus, which represents the upper bound, is equal to xt of dot plus delta plus, and xt of minus, which is the lower bound, equal to x dot of t plus delta minus. Now we need to design, or we need to calculate these two bounds, and these two bounds, the deviation from the actual states of the system, these bounds delta of plus and delta of minus will reflect the deviation from the actual states of the system. Okay, so delta of positive is equal to gamma positive plus gamma positive of v, gamma positive of phi, where this represents the upper bound value on the measurement noise, and this represents the upper bound value on the measurement noise. And this represents the upper bound on the state disturbance, and this represents the upper bound on the measurement noise. And these two combined give us the upper bound for the upper bound on the system state disturbance plus measurement noise. Similarly, delta of minus is equal to gamma minus of pi plus gamma minus of v. It gives us the minimum bound. So now we need to know what is lambda plus of pi and lambda plus of v, and similarly lambda minus of pi and lambda minus of v. So we define these values here. Lambda plus of pi is equal to zeta plus pi d plus minus zeta minus pi d minus. So it will give us the lambda of positive. Similarly, lambda plus v, we will get the upper and these are the d represent the n minus 1 concatenation of the maximum values on the state disturbance, where we represent the n concatenation of the maximum value on the measurement noise of the system. Similarly, we get the lambda of minus and lambda minus of pi and lambda minus of v. Now, all these values, in order to get what we need to know the zeta positive and zeta positive of pi, zeta positive of v, zeta positive, zeta minus of pi, and zeta positive of v. So what is zeta is n into n cross n into n minus 1 matrix, which is equal to lambda of 2 minus lambda of y of t lambda of pi. This is called the disturbance matrix, and zeta of v represent the noise matrix, which is equal to minus lambda of y of t. So the lambda of y of t is already defined above, which is the output matrix. So the negative of the output matrix will give us the noise matrix, and lambda of 2 is equal to product of eta of t minus 1, eta of t minus 1, I is equal to 1 into n minus 1, where I this eta lambda of pi is also equal to this matrix 0 0 0. This is vector or matrix C, output matrix C 0, and C zeta of t minus 1, C zeta of t minus 1 into zeta of t minus 2, where zeta of t minus 1 is a naught plus delta a theta of t minus 1. So this is the matrix given in the system, for the given LPV system. So in order to use the proposed interval estimator, we need to know the first n-1 values. For example, if our system is of the fourth order system, so in order to use this proposed interval estimator, we need to know the first three state values, like n is equal to 4, then for n is equal to 0, n is equal to 1, and n is equal to 4. So then we need to know the first three values, 0, 1, and for t is equal to 0, t is equal to 1, and t is equal to 2. So for that purpose, we propose the interval predictor. So the first n-1 input and output values of the system must be available to apply the proposed technique. If we want to apply the proposed interval estimator that we proposed above, we need to know the first n-1 values. So if, for example, for n is equal to 5, so we need to know the first 4 input and output values. And so to get the first 4 or n-1 values, we use the following interval predictor, which will give us the tight initialization. Like our interval estimator will be more closer to the generated interval will be more closer to the actual state. So the interval predictor that will generate boxes or interval vector, which will contain the exact value of the states for all t less than or equal to less than n-1. We use the following recursive interval equation to get the first n-1 output and input values. So x of t box or interval is equal to product of L equal to 1 up to t, a of t minus L, x of naught plus chi of t minus 1 plus zeta zeta of t minus 1 and plus eta of t minus 1. Chi of t is equal to a of t chi of t minus 1 plus phi of phi box, which and eta of t is equal to a of t eta of t minus 1 of k minus 1 plus b of t u of t, where chi of naught is equal to the bound on the disturbance, and eta of 0 is equal to b naught u naught. It will be the first value of the matrix B and the initial input value. So this recursive interval equation will give us the first n-1 values for applying the proposed interval estimator. Okay, so now we will present the theorem that if all the assumption 1, 2, 3 means the system must be observable, at least full column rank, the unknown values, the uncertainties, and the disturbances must be bounded, and the n-1 and n concatenation of the values will be given. Then we will use the following theorem. The proposed interval estimator will give us the upper bound and the lower bound and upper bound estimation for all t greater than equal to n-1 of the actual state of the system, such that x of t is greater than or equal to x of t minus and less than or equal to x of t plus, means the upper bound and lower bound. The actual state will always be inside these two bounds. Moreover, the width of the two estimated states are bounded by, and this equation will give us the system stability, that the proposed given model or the proposed given interval estimator will be stable if the width of the estimated the width of the generated interval is less than the infinity norm of the disturbances, also into the width of the disturbances plus the infinity norm of the measurement noise into the interval width of the measurement noise. So now in order to prove the proposed interval estimator, the given LPV system can be written as, this is the this is the given system, the given LPV system. We can rewrite the given system into x of t is equal to product of eta of t minus 1 into x naught plus summation j equal to 0 up to t minus 2 product of I equal to 1 up to t minus j minus 1 eta of t minus I into bu of j plus phi of j plus bu of t minus 1 plus phi of t minus 1. And similarly, we can rewrite this equation by x of t is equal to product of I equal to 1 up to n minus 1 eta of t minus 1 into x of t minus 1 plus x of t minus n plus 1 plus summation of j equal to 1 up to n minus 2 into product of I equal to 1 up to n minus j minus 1 into eta of t minus I, and with product of bu of t minus n plus j plus pi of t minus n plus j plus bu of t minus 1 plus pi of t minus 1. And then using the interval analysis theory, we can write this equation. We can replace this equation using the interval analysis theory by this equation. That is x of t box, which is an interval, is equal to product of n naught plus delta of a theta of t minus I. This theta of t minus I is equal to this. In this equation, theta of t minus I is a naught plus delta a t theta of t minus I. And this is a box, so we can write this is also an interval. Using interval analysis, we can write that x of t minus n plus 1 are equal to this, plus lambda of 1 into sigma of u t minus n plus 1 up to t minus 1 plus lambda of 2 into d. The product of these values, this one, product of these two will give us this one, this term, and the product of this, which is already explained in the above slides, it will give us these values. So now the only thing in this equation is we don't know this bound. So we need to know calculate this bound and put that bound in here. Then we will get because all these values except this one is known. So we just need to replace this with another equation. So previous input output values give us the following result. So this represents the previous input output values. Like for example, if we have t is equal to 4, so here we will have the x of t minus 3. Or if t is equal to n is equal to, if we have a three-dimensional system, then it will be t minus 2. So we need to know the first two values. So this equation will give us the previous input output values, which is lambda naught of this is the inverse of the observability matrix, sigma y of t minus n plus 1 to t minus 1. These are the previous input output values, minus lambda of c sigma of u of t minus n plus 1 up to t minus 1. This is the previous input values, minus zeta of pi into d, and this already we already defined this matrix in our initial slides, that this is the n blocks of the output vector. This is the n blocks of the input vector, and this is the n blocks of the output vector, which is given by this. So finally, we can replace this term with this equation, with this one. So finally, we will get x of t is equal to lambda of y of t sigma of y into t minus n plus 1 up to t minus 1 plus lambda of u of t into sigma of u of t minus n plus 1 up to t minus 1 plus zeta of pi into d, which is this is the disturbance, and this is the measurement noise. We already defined these terms in our previous slides. So we just need to put this equation here and then this equation here, and we will get these results. So in order to show the stability, or kind of it is similar to the stability analysis of the simple interval observer methods, where we need to show that the system should be observable. So in our case, the system should be bounded, and for bounded, we need to know that the interval width of the estimated state should be less than or equal to the upper bounds of the measurement noise and the disturbance matrix norm of these norm of the measurement noise and the norm of the disturbance matrix. So the finite time convergence of the interval width is one of the primary issues concerning the tight initialization and stability of the interval state estimator. So if we go to the step 3, where we define the interval width for the system here, this is the first, because in order to apply the proposed interval estimator, we need to know the first n-1 values. So before applying, we will use this interval predictor. So for that reason, we need to know the width of this interval predictor. So the interval width for step 3 will be width of xt minus up to, it is an interval vector. So it is less than or equal to the product of the L equal to 1 up to t a of t minus L, this infinity norm of this matrix, into width of the initial value plus width of the h of t minus 1. The interval width for the proposed interval estimator. This equation is the interval width for the interval predictor, that is for all t less than n-1. And the interval width for the proposed interval estimator, which is given here, this one, this we need to show that the interval width of this equation is always less than this one. So width of this one is equal to the zeta of t infinity, or width of d disturbance, plus zeta of v infinity norm, width of the v. So it follows that from this we can easily define, we can say that the width of this term is less than the interval width of the given disturbances and measurement noise, because these are the optimized measurement noise, and these are the optimized disturbances, as we already calculate these widths in our previous slides. So if this it shows that this is always less than these interval widths, so we can directly and our this width is less, the width of the interval vector is less than these terms, so we can directly say that this width of the proposed interval is less than the these values of the measurement noise and the disturbances. So this equation gives us the stability criteria for the proposed interval estimator, and we will see this. We will show this criteria or this stability in our simulation as well. Okay, then now we need to we just try to extend our interval estimator, design interval estimator. We just extend our proposed interval estimator model to the SEIR epidemic model, because nowadays the epidemic models are very important, especially in now is because of this COVID-19. This is also it is also an epidemic, and it is also almost similar to the SEIR epidemic model already proposed for the previous epidemics or previous outbreaks, just like Ebola outbreak. So we That's why we take this model in order to estimate the states for the system. So after estimation, we can estimate the outbreak, and after estimating the outbreak, we can make any strategy to maintain the situation under control. So this is a fourth order. Our model is fourth order. This is a non-linear fourth order SEIR epidemic model. This one represents the dynamics of the susceptible individuals. This represents the dynamics of the exposed individuals. This is the infectious individuals dynamics, and this one the recovered individual, recovered human. Like we already explained what is susceptible. Those people who are not yet infected but can infect in future. Exposed, those people who are infected but cannot infect others. Infectious, or those people who are infected and can infect others, and this one is like they are infected but they are recovered and they are immune now. So these are the dynamics of the SEIR epidemic model. So where S of k, or R of S of k, E of k, I of k, and R of k, these are the represent the state variables in each model. A is an very uncertain quantity, which represents the natural birth and death rate, it represents the increase or decrease in the population. And all these B, C, and D, these are unknown but bounded uncertain transition states. We didn't know the exact values of these, but we only know the bounds on these transition rates, where delta of k is the unknown time varying transition rate. This is unknown and unbounded. In our case, we take it as unknown and unbounded. So we need to calculate this as well. Okay, the noisy counts output measure data of susceptible individuals. We represent this as our output measurement, where y of k is equal to S of k plus V of k, and we didn't know how many people are recovered, how many people are still infected, how many people are still exposed. So that's why we use this measurement noise. We didn't know the exact values. Okay, so the SEIR model and output can be written in terms of, if we transform the given model, this model, to the standard state space dynamic model. So we can represent the given model as x of k plus 1 is equal to a of k, x of k plus e zeta of k plus w of k, y of k is equal to c x of k plus v of k, where w of k is the state disturbances while converting the system dynamics, and v of k is the measurement noise. X of k is the vector of this state vector, which represents the variables s, e, I, and r, the unknown state vector. Zeta of t is the uncertain input. This represents the uncertain input, which is highly uncertain and unknown, which is equal to delta of k, s of k, I of k. A is the, in this case, A is the time varying, and it depends upon the these values. It depends upon the natural birth and death rate, and the transition rates A, B, C, and D. So in our case, A of k is also time varying, while E, C are constant matrices. W and V represents the unknown but bounded disturbance matrix and noise matrix respectively, and they are defined below. So A of k from this system, if we replace this system with this one, so we get A of k equal to 1 minus A of k, which is time varying, 0, 0, B of k, 0, 1 minus A of k, 0, 0, minus C of k, 0, C of k, 1 minus A k into 0, minus D of k. These three terms are one element. These one, and similarly 1 minus A of k minus D of k is one element, and 1 minus A of k minus B of k is one element. So, and we get E is equal to minus 1, 1, 0, 0, and C is equal to 1, 0, 0, 0. Okay, the W of k, which is the disturbances, is equal to A000, and its upper bound is the minimum value of A000, and lower bound, sorry, and upper bound is A of maximum value of A000. And similarly, we know the upper and lower bound of the V. So the interval estimator designed for the already designed LPV system can be applied directly to the SEIR Epidemic model as below. Here we use the decharacterization of the system, and we convert to this model. Okay, so x up of k is equal to x cape, or x. This stores these states, estimated states. So x cape of k equal to lambda up of k d up, and v upper bound x lower bound is equal to x cape of k lambda lower bound plus d lower plus v lower, where lambda up and lambda low is the is a 4x1 matrix that represents the upper and lower bound and the uncertain input. D upper and D lower is the 4x1 matrix, which represent the upper and lower bound, the uncertain birth and death rate. And similarly, V up and V low belongs to our 4x1 matrix, upper and lower bound, and the measurement noise. So now the most important thing is we need to calculate these bounds, so then we can get the upper and lower bounds on the estimated states. Okay, first the bounds on the uncertain input. This is the uncertain input, and we need to calculate the upper and lower bounds on these uncertain inputs, which is equal to phi e of 3 plus zeta of upper of k minus phi e of 3 minus zeta of k. And similarly, lambda lower is equal to pi e of 3 plus zeta low of k minus pi e3 minus zeta of k. So if we see from this matrix, from here, y of k is equal to c x of k plus v of k, we can write y of k plus 1 is equal to c x of k plus 1 plus v x of k plus 1. And from here, x of k plus 1, we can put the value from x of k plus 1 to here. So we will get this equation. And from after solving this equation and putting these values, CE is equal to C and E are vectors, non-constant vectors. If we multiply, we will get -1, and CW of k, we will get A of k. And putting all these values, finally we'll get zeta, because in this matrix all values are known except this zeta. So we use this, and we will get zeta of k is equal to C A of k x of k plus A of k minus y of k plus 1 plus v of k plus 1. And then we can put we can write we can expand this into upper and lower bounds and put here. So the upper bound of zeta of k will be equal to CA of positive x of up of k minus CA of negative x low of k plus mod of minus y of k plus 1 plus v up plus A up. And similarly, zeta low is equal to CA positive x low of k minus CA negative x up of k plus mod minus y of k plus 1 minus v up plus A lower. And such that we see that zeta of k will be equal to lower and upper bound. It will be inside this. This represents upper and lower bound. And E3, where we put here E3, which will be equal to E3 is equal to E and E, because we need the system, all the system should be in same dimension to get the products of the vectors and matrices. Okay, now we need to know the bounds of unknown birth and death rate. We calculate this one now, or this one, and then next one we will calculate these bounds. So bounds on the unknown birth and death rate are given by, which is equal to pi of plus k w upper bound of 3 plus pi minus W lower. Similarly, D low is equal to pi up positive means upper, W lower of 3, pi negative and W of 3. Now these W of 3 represents 12 cross 1 matrix, because our system is of the 4th order matrix. So we will get these denotes the concatenation on uncertain birth and death rate. That's why we say that the state disturbance is n-1 concatenation. So it represents the n-1 concatenation. W of 3, W of 3 of upper is equal to W upper and W upper. Similarly, W3 lower is equal to W lower value and W lower value. These are the minimum values and these are the maximum values. Similarly, zeta positive of k is equal to maximum, which is very similar. It's similar in the interval analysis theory, that it will represent the maximum 0 of pi of k. Pi of negative of k is equal to maximum 0 minus pi of k, and pi of k is equal to sigma a minus delta of y, sigma ca, where sigma a can be obtained using this matrix, where zeta 1 zeta 2 zeta 1 3 1 4 1 5, these are all defined here one by one. They are given below for all the values. Similarly, sigma ca will represent this matrix, where 0 4 cross 1, it means a vector of dimension 4 or 0. Similarly, 0, and this will be 12 cross 3 matrix, with k is equal to k minus 1 and k2 is equal to k minus 2, because the matrix is too big. So that's why we put k1 and k2 here, just to make it short, and it will be fit inside the slide. Similarly, we need to know the upper and lower bounds on the measurement noise, which is equal to V up is equal to pi positive V of k V4, pi plus 5 negative of V of k V lower bound of 4. Similarly, V lower bound is equal to pi positive V of k V lower of 4 plus pi V of minus of k V up of 4, where V4 represents the n concatenation of the measurement noise vector, which is 4 cross 1, denote bounds concatenation on the noise as follows. V4 of up is equal to maximum value of V, and V4 of lower represents the minimum values of 4 concatenation, like n concatenation of the measurement noise vector. And we need to know this. So phi of V of k is equal to maximum 0 pi V of k, and phi V negative of k is equal to maximum 0 minus phi V of k, and this phi V of k is equal to the negative of the output matrix. So similarly to the LPV model, for that we will represent a theorem. A similar theorem can be represented here. When assumption 1 is satisfied for the given SEIR model, thus assumption 1 is that the given model should be observable, or at least it should be full column rank observable. So when assumption 1 is satisfied for the given SEIR epidemic model, which is a 4th order nonlinear model, the proposed interval estimator will give the following equation. Because n is equal to 4, so the proposed interval estimator will estimate the states from for k greater than or equal to n minus 1, which is n minus 1 is 4 minus 1 is equal to 3. So the proposed interval estimator will generate the states upper and lower bounds for the actual state, such that x of k should be greater than or equal to x lower bound, and it should be less than or equal to x upper bound, provided that the initial condition or these initial conditions are satisfied. So if the proposed interval estimator provides the upper and lower bounds for k greater than or equal to 3, so what about 0, 1, 2? So the 0 is because we know the initial condition. For 0, it is not a big problem. So only we need to know for 1 and 2. So we use the given interval prediction for k less than 3. for k equal to 0, 1, and 2. So to run the proposed interval estimate, we need to know the first n-1 values of the input and output, which is not always available. So that's why we need to use the interval predictor. And we use the following recursive interval predictor that will give us the first initial bounds on the actual states of the system, such that the actual state should be inside between these generated bounds. So the following interval predictor generates x of k. It will generate an interval vector such that for k is equal to 0, 1, 2, we have the actual state is always inside between these generated bounds. And this recursive equation will provide x of the vector x of interval vector x of k for k is equal to 0, 1, 2. So x of k bound is equal to L is equal to 1 up to k, a of k minus L, x of 0 plus del of k minus 1, or del of k is equal to a of k, del of k minus 1, e zeta plus w bound, zeta bound, and zeta of 0 is equal to e of zeta bound plus v w bound. So similarly to the LPV system, the finite-time convergence, the primary issues concerning the tight initialization and stability of because the primary issue for designing any type of observer or controller, we need to the primary issue for that is the stability. So we propose the following lemma to compute the upper bound on the interval vector. The following inequality determines the upper bound on the breadth of the interval vector, provided that the proposed interval estimator and predictor for all k is greater than or equal to 3. So this lemma will give us the upper bound on the interval vector. So it will show that it will give us the upper bound value, and from that we can say that the proposed interval estimator is bounded. Okay, we didn't show proofs of these interval, this theorem, this interval predictor, and this finite-time convergence because of the two reasons. Reason one is that it is almost similar, not exactly similar, but almost similar to the LPV system. And number two, because these results are not yet published, so we are waiting for that. And it is under accepted, but with minor review. Okay, now in order to, for any interval estimator design, for every design method, if you design interval estimator or controller, we need to show the performance of the proposed technique compared to the other techniques, and we need to show how it works to show its performance. So we use two examples. One is for the LPV system, and the other is for SEIR epidemic model. So we need to show we have non-cooperative LPV system with multiple outputs. We have multiple output system. We have two output system, which we are using the OIBO technique. The unknown but initial condition, noise, and state determinant are respectively given as thus. They are the initial values and conditions. This is the LPV matrix exogenous, stationary, non-stationary values. This is the measurement noise values, which is disturbance state disturbance values, which is unknown but bounded. And we get these results by simulating these matrices. We can see that the actual state is always inside these two bounds. And here we show the finite-time convergence because our proposed system is of the order 3. So here we see that after third iteration, our bounds, our interval width is always less than the upper bound value of the given measurement noise and disturbances. Similarly, we take this example from the Ebola outbreak. Ebola outbreak came into the West Africa. So where A is equal to, these are the transition values. A is the matrix, the non-matrix, unknown and bounded values, or these are the initial conditions. These are the measurement noise which are unknown but bounded. So after simulating all these equations, we get these matrices in order to run our proposed interval estimator. The system is of order 4. So first we use for k is equal to 0, 1, 2 the proposed interval predictor, and then after that we use the proposed interval estimator to get the guaranteed bounds. So if we see, we compare our proposed method with the SEIR epidemic model given by interval estimation given by this 16. So we see that our bounds are always very the proficiency of our technique is far better than the one given by 16. All these bounds shows us that the proposed method is performance is better than the one given in the 16. And these are the errors of the estimated bounds. So if we see that our error, these show the pink shows our errors and the blue shows the error produced in 16. So if we see that our model is always better than the one proposed in 16. So we proposed conclusion. Finally, we came to the conclusion. We proposed the interval estimator for the LPV and SEIR epidemic models that are subject to disturbances and measurement noises. The proposed method is designed on the observability metrics. That's why we use the observability metrics in order to avoid these strong and strict cooperativity condition. And we also save the computational time. And our method, as we can see from the example 2, that more accurate compared to the other matrices. And all these the proficiency of the technique and its accuracy is given by the 2 simulation examples. Okay. So thank you. These are the references that we are used in our presentation. So thank you for your attendance and for your patience for listening to me. If you have any questions, so you can ask.
Okay, then many thanks for your quite detailed presentation. And yes, since you just mentioned, if there are any questions from the audience, please go ahead and ask them. So there's currently no one in this audience here who wants to ask a question, but unfortunately, one of my colleagues, Tarek Raisi, unfortunately, he already had to leave because you have been quite long with your presentation. And he sent me 2 questions by email.
Okay.
And maybe let me ask them. The first question that Tarek wanted to know is, for him, the stability analysis of your observer hasn't been quite clear. And yes, one of the aspects why he's asking this question is you don't have any degree of freedom like an observer gain that you can tune in order to ensure asymptotic stability. Maybe you can comment on this. Okay.
It's true that we don't have an observer gain to tune our observer in order to show the stability exactly. But if we see from here, we show the stability of this system in terms of the interval width, and then we already also simulate the width stability in our simulation. Okay, from here, this one, if we see the width, this is the width of the generated bound is always less than the infinity norm of the interval predictor for because as we mentioned that the proposed method, the proposed interval estimator, if we know the first n-1 values, then we can apply the proposed method. So in order to, if in some cases, if we don't have the first n-1 values, we need to run the interval predictor. So we also need to show that the interval predictor width of the interval predictor is always less than, is bounded and is less than the norm of the measurement noise and the disturbances. And similarly, for the interval, for the proposed interval estimator, the width of the estimated bounds is always less than, the infinity norm of the measurement noise that we already calculated, and measurement noise and state disturbances. And if we didn't these are the norms of the interval state disturbances that we are calculated. If we take the norms of the given that are given by the system, that if we take the norms of the measurement noise and the state disturbances, it is always greater than the one defined by that we described.
I think this reasoning is clear, but if we are having a look at the very first line of the slide, you have this product of some matrices of your dynamics matrices of the system. And what would be happening, for example, if the system model itself is open loop unstable? You're multiplying different matrices A of t.
Yes.
Those interval matrices depend obviously on some uncertain parameters, on uncertain time varying or arbitrarily varying parameters. And if the open loop dynamics is unstable, you're multiplying such matrices. Wouldn't this lead to some kind of blow up in the width?
No, if we see the simulation, if we see the simulation of the system, then
yes, but your system is open loop stable.
Yeah.
Yes, you have some Bieber stability of your open loop dynamics. But what would be happening, for example, if your system matrix A in the discrete time model contains eigenvalues outside the unit disk?
Then maybe you are right in that case, that the if we multiply different matrices, so then it will make a problem. But the thing is that we are just using the state disturbances and measurement noise to generate the bounds. We didn't use the matrix A or any kind of matrices to generate the bounds. In order to generate the bounds, we only use the measurement noise and the state disturbances. The matrix A and the states we just use for the input to generate the input and output blocks, and these input output blocks. Let me show you. Just like here, we just convert the same model into input output blocks, and from this input output blocks we just get this state. From here we get this state into these are the output values, these are the input metrics, and finally these input output blocks we use to estimate the states. So this is almost exactly the same system, we just transform the same system into the input output blocks. So I don't think it doesn't have any problem with the matrix A.
Yes, and since you just showed this this generalized inverse of the observability matrix here on this slide, if you have uncertain parameters in the matrix, how do you define this pseudo inverse?
The uncertain parameters where?
Yes, the matrix lambda O. The matrix lambda O depends on your system matrix, on your dynamics matrix A.
Okay.
You have uncertainty in the matrix. This matrix lambda O is an interval matrix.
Uncertainty where? You mean this delta matrix?
No, the matrix lambda O.
Yeah, this one.
Yes, this one. It
depends. This is the generalized.
Yes, it depends on the system matrix. And if you have uncertainty in the matrix, you have to compute the pseudo inverse of an interval matrix.
Yeah, we will use.
How do you do this?
So
because I think this strongly suffers from the wrapping effect of interval analysis.
Yeah, but because in my case I didn't take the uncertain parameters in the input matrix A or C. because they are just like the known matrices, and there is no uncertainty in these matrices.
Yes, but I think, frankly speaking, for example, for this epidemics model, you have quite strongly uncertain dynamics.
No, in epidemic models, here we see that the values of A, these are uncertain, but they are bounded.
Yes, but then the observability matrix is again an uncertain matrix, which is bounded, and you have to compute the inverse.
Yeah, we need to, but it just transforms this matrix A into a linear time variant, this kind of LTV type system. It doesn't make it unstable or something like that. We can say that this is just like even I say here it is a time varying matrix. This is just a time varying matrix because we know the values of A, B, C are the bounded values, not the exact values. So these are bounded.
Yes, they are bounded, but is it really guaranteed that the matrix stays invertible? Just by multiplying uncertain parameters at the end.
Yeah, maybe.
I think
yes,
it's not purely the observability, the criterion, but it's really invertibility of the observability matrix under the constraint that you have multiplied already some interval matrices.
Yes, it's true. And the matrix, it's not true. It's not that the system should be fully observable. It may be just full column rank observable is also okay, like a column.
Yes, okay. And then in my list of from the email of Tarek, I have a further question. And his further question was concerning theorem 1.
Theorem 1. Okay.
Yes, and he asked if there are some relations to L infinity performance criteria.
L infinity no, we didn't discuss the L infinity performance here.
And do you think that there are relations to the L infinity performance?
I don't think there is any relation because this is just if maybe he think about this infinity norm.
I think he thinks about this infinity norm that you can see there, and typically when you're using typical L infinity performance criteria in the classical interval observer design, you're using this norm to tune some observer gain at the end.
Yeah, but that's why maybe
the question is if there's some relation. Maybe you could also define some kind of norm here in order to tune your performance, or is it really just given by the system model, you end up with some width on the uncertainty of the states, and just that's it at the end?
I think the L infinity is the minimum because we use the width criteria to show that the system is bounded. So L infinity we use here because this is the minimum value the minimum bound value they can give us. So that's why we use this L infinity criteria over here.
Okay.
But it doesn't. Maybe it's not. Maybe he is thinking in the other traditional type of interval observer technique where we use the L infinity criteria to tune the observer.
Okay. I think if he has further questions, he will send you an email.
Okay.
And do we have anyone else here in the audience who wants to ask a question? Okay. I think this doesn't seem to be the case. I have one final question at the end.
Okay.
In your epidemics model, you assumed that you can, I'm thinking of the output equation. I think it's the next slide.
This one.
Yeah, yes, this one. You have, this proportion of the population of the susceptible as humans or whatever species here. And you assume that the output equation is directly a measurement of S plus some additive disturbance or uncertainty. Typically, I think you may underestimate or also overestimate the percentage of susceptible species. What would be happening if you have a multiplicative parameter in the output equation, a parameter multiplied with S, where this parameter is some interval quantity, meaning in this case, you have really some, yes, let's say some unknown percentage at the end that you cannot quantify directly.
So,
your approach would work again at the end, or what's your recommendation?
I didn't work about it, but because I take this model from the Ebola outbreak. They use the same model for their epidemic model. So in that case, in my case, because we the susceptible individual, because we represent, because we don't know how many people recovered, how many people infected, or how many are exposed. So this represents that.
Yes,
but,
and it's also
and
almost impossible to correctly measure the number of susceptible persons, because just think of, let's say, we here in Germany, we want to model the COVID-19 situation. We have around 84 million persons. And definitely you cannot test all of those 84 million persons.
Yeah.
That means you're just testing some percentage of the people. And at the end, this also leads to some uncertainty in the measurement of the susceptible persons.
No, the susceptible
that I would
people...
measure or model in some way with a multiplicative uncertainty there.
No, the susceptible people, because the infected people, we know the infected people because after testing. The exposed people...
You also don't know them perfectly. You have just a subset of the infected that is being tested, and
yeah, these are the
you
people
don't
who are
know
tested.
them exactly.
Yeah, so this may be, but in my case, I just take it because I say that we know the number of susceptible people, but it's disturbance we didn't know.
Yes, this was your assumption, but the question is, if you have uncertainty in the output matrix C.
No, but then maybe then we will hear if we know this value. So the matrix because we mainly use observability metrics to use this technique. So here the observability metric is square. Maybe in that case it will not be a square metric. So then we will use just the generalized metrics for taking the inverse. You mean the product with this?
It's a product. It's the output matrix C will contain an interval parameter at the end.
So maybe then this we will have multiple outputs.
No, it will still be a scalar output, but you have in the matrix C, there will be an interval quantity instead of the point valued quantity that is equal to 1. Your output was 1, 0, 0, 0.
Yes, 1, 0, 0, 0.
Yes, and my proposition would be you have something at the end. The first entry is an interval. You have, for example, something 0.9 till 1.
Okay, yeah.
And does your approach work at the end?
Maybe, but then maybe we can take the average of that or something like that. Or the mean?
No, I think taking the mean doesn't make sense if you want to perform something like a guaranteed estimation.
Yeah, this is true. I didn't.
Maybe it's just a recommendation for future work.
Yeah, it is recommended, but I didn't know, and to be honest, I didn't know, and I didn't think about that.
Okay, good.
Yeah.
Is there anyone else who wants to ask a question? If not, many thanks again for your presentation, and also many thanks for answering all the questions that we have asked.
Okay, thank you.
And
thank you for inviting me.
Yes, it was a great pleasure having you here. And now I just want to advertise for the next seminar. Our next speaker on Friday in 2 weeks will be Paul Krüger, who is also present here in the audience. And yes, we'll be looking forward to Paul's presentation in 2 weeks. And to all of you, have either a nice Friday evening, afternoon, or even Friday morning if you're somewhere in the
Friday night here.
And yes, for all of you, have a nice weekend and see you soon in Friday in 2 weeks.
Thank you. Thank you so much.
Bye-bye.